Unmanned surface vessels are becoming more prevalent in our world for uses such as security and surveillance, and often operate alongside manned surface vessels. This introduces the need for them to be controlled safely and accurately, despite the complicated hydrodynamics of water, as well as the challenges of environmental disturbances, such as winds and currents. A common configuration of USV is a vessel differentially driven by two rear thrusters. This setup is underactuated for holonomic control, and actions like strafing and heading hold station keeping are either not possible or reliable to perform. Adding bow thrusters to this common configuration allows the system to be fully actuated for full holonomic control. The aim of this thesis is to produce a control solution that allows a USV configured with bow thrusters to perform holonomic control. This is to be extended into station keeping and path following activities. A solution is achieved by using a carrot following algorithm to produce a desired waypoint and heading. From the desired waypoint and heading, a desired linear and angular velocity is generated. A control law based off the hydrodynamics of the system turns the desired velocity into desired force and torque on the system. A force allocation matrix solves the desired force and torque into individual forces for each motor in the system. The corresponding motor command is generated by inverting the thrust curve of the motor. The calculated motor command is then applied to simulation. The USV is a wave adaptive modular vessel by Marine Advanced Robotics. It has two back thrusters with two front bow thrusters to be fitted. Based on the intended integration with physical hardware, the angles and positions of the rear thrusters cannot be altered, but the static angles of the front thrusters can vary. Forces generated from a motor are not proportional to the corresponding motor command. Thrust curves provided by the simulation were used to calculate the corresponding motor command for a desired force. For different thrusters outside of simulation, a bollard pull test can be used to determine these thrust curves. A force allocation matrix was used to define the relationship between the forces the motor provides to the total force and torque applied to the vehicle. This force allocation matrix can be inverted using the pseudo-inverse, and the equation rearranged so that the corresponding motor forces can be found for a desired force or torque. Ordinary differential equations were generated to define the system in surge, sway, and heading rate space, modeling the hydrodynamic effects from added mass and linear damping from the water. From this, a control law was developed to produce a force and torque from desired surge, sway, and heading rate. The performance of the developed control law was assessed against a PID controller. The controller was tested in varying demands alongside different gains. Testing was also extended into varying disturbances such as winds and currents. Overall, the produced control solution was very stable and responsive under all scenarios, whereas the PID control solution would either be very easily to oscillate and be unstable in certain scenarios, or require a very low proportional gain. In a scenario with stronger winds, the produced solution would exhibit a steady state error. This was not present in the PID solution. A proportional derivative controller was used to generate a desired velocity from desired position and heading. This was used to allow the system to station keep and maintain heading. A carrot following algorithm was used to feed the waypoint following controller desired positions and headings to follow. A desired path is discretized into a series of waypoints. The carrot following algorithm will then take a radius around the vehicle and set the desired waypoint as the closest point outside of this radius. This thesis contributes the following: an implementation of a force allocation matrix, a holonomic velocity control law for a USV, and a path following and station keeping solution. This work can be extended and paves way for future research, some of which could include implementation onto a physical system, accounting and measuring disturbances such as winds and currents, and an exploration into trajectory following, where a path timeline is adhered to.